Okay then, so we've processed our data, everything looks pretty nice and spiffy, a couple of little holes here and there, but there's nothing to worry about. But why is it all angled so funny relative to our coordinate system? What's going on there? Now it's actually done that because I didn't check a box before, which would have done an auto plane fit based on this plane, but I've done that for a reason. It's just purely to explain a little bit more behind what the software does. The cameras, well, the software knows the position of those cameras, and it does that through the calibration procedure. But what the software does is it determines the x-axis by looking at the position of the two cameras and saying, okay, I'm just going to draw a line between those two cameras, and I'm going to call that the x-axis. The z-axis, it does that by defining it as being normal to the x-axis, but also in a inward and outward direction relative to the cameras. And then the y-axis is just defined as being normal to both of those too. And so by default, with nothing else happening here, you end up with some funny little numbers here. And the reason why I'm actually looking at the z coordinates here, the actual z variable, and it's actually showing that the bottom here is closer to the cameras than the top was. So therefore the cameras would have actually been sitting below the center of this specimen and would have been looking up at the specimen somewhat. But anyway, what we can do now is we can change the coordinates, or change the orientation of the specimen relative to the to the coordinate systems and try to make them synchronized. So if we go to Data, Coordinate Tools, select Coordinate System, and the one that I like best is the 3-point selection because it gives you the most flexibility with what you're doing. So a 3-point selection, obviously you select 3 points. The very first point you select will actually be an origin, and I'm going to select it there. The second point you select will determine the positive x-axis. I'm just going to make sure it's as straight as I can here. That looks pretty straight to me. So I've now said that x is positive in that direction. And y, I'm going to say is positive in this direction. I'm going to make that as straight as I can relative to the specimen as well. That looks about there, I'd say. And I click accept. Now for the transformation, I'm just going to say x, y, z, 3 points. Okay. Do I want to apply the transform to all data? Yes, I do. Select yes, it's going to have a think about it. And whoa, what's going on there? Well, actually, this is a good thing, because if you have a look at our Z, I'll just move this around, have a look at our Z scaling, what it's showing is it's showing between 0.08 millimeters and minus 0.11 millimeters. So it's showing a, what's that, 0.2 millimeters variation over the entirety of the specimen, which is, what's that, 260 to, so about 260 millimeters by about 80 millimeters. So it's showing a 0.2 millimeter variation on that, so that's pretty damn good. Unfortunately though, it looks a bit ugly. So one thing I like to do is over here, if we remove auto rescale coordinates, then change our Z scaling to something which is a little bit more realistic, say -5 to 5, you'll find that those numbers flatten out very quickly, and that looks a little bit better. And so everything's looking much flatter and much nicer now. But a question I might ask is, what's with this line here and what's with this line here? Well, that actually comes from our specimen itself. There was actually 2 different dotting systems applied. The student who these tests were carried out for, he applied texture dots, and I'm not a fan of them, so I applied a paint dotting over the top of this for my own purposes. And what you're seeing here is actually just literally it's the thickness of the ink of the texture dots. It's just ever so slightly different to the thickness of the paint. And so that's what you're seeing there.